Nice to meet you everyone. My name is Tomohiro Oishi. Now I'm a postdoctoral fellow in the University of Zagreb, Croatia. Today I'm talking about the proton emission from hypernuclei. My interest in this talk is simple. That is, whether this lithium lambda 6 nucleus is bound or not. And actually, this problem is closely connected with the effective interaction between lambda and proton. But this lambda-proton interaction has been unknown because the direct two-body scattering experiment is impossible. But okay, let's remember that its subsystems are, first, alpha and lambda particles can be bound, and their binding energy is well known as -3 MeV approximately. On the other side, alpha and proton particles cannot be bound. Instead of the binding energy, they have the so-called resonance energy about 2 MeV, and their one proton width is really large, about 1.5 MeV. So we can consider two scenarios. If the interaction between lambda and proton, or so-called YN hypernuclear interaction, is strong enough, this three-body system can be stable against the one-proton emission, namely alpha and lambda particle cooperate to bind the last proton. On the other side, in the scenario 2, one proton emission can happen. Alright, so now let's consider this lithium lambda 6 nucleus as the three-body system composed of alpha, lambda, and proton. Here, I fix the three-body total Hamiltonian written like as this, and this Hamiltonian is written in the so-called V coordinates. And in the bottom half of this slide, I gave a brief formalism to derive these V coordinates. And please also notice that the center of mass degrees of freedom is well separated. And inside of this Hamiltonian, of course, we have the interaction between alpha lambda, alpha proton, and lambda proton. First, for the alpha lambda and alpha proton potentials, I adjusted those parameters to reproduce their resonant and bound energies, respectively. That is about 1.7 MeV and -3.1 MeV. Now I'm almost about to present my result. But before that, let me explain also the proton-lambda interaction, which is the last piece in our three-body Hamiltonian. For this interaction, in this work, I employ the zero-range potential, and that is described by this delta interaction, and its strength parameter is adjusted to reproduce the scattering length about 2.2 Fermis. And this is so-called empirical result predicted by several theoretical calculations. And in the left side of this slide, I plot the decay probability of one proton emission. Because one proton emission is an open quantum phenomenon, the time-dependent calculation can be a powerful tool to investigate. And here I plot the decay state distribution at 500 Fermis and 1000 Fermis in the unit of CT. Okay, let's watch this time-dependent process. First, one can notice that along the y-axis for lambda distance, there is no trajectory. So this means that lambda particle stays around alpha particle. He does not escape. On the other side, along the x-axis for proton distance, there is a finite trajectory, and this means that proton goes out. Namely, proton can be emitted from this three-body system, whereas lambda cannot be.
Next, I show you the results on their connection between one proton emission probability and the effective interaction between lambda and proton. As I said, I employ their delta function interaction for lambda proton. And here I tried the two cases of 1 minus and 2 minus states of the three-body system. And in the left-hand side panel, I show the three cases, namely case 1, 2, and 3. And here, I tried several sets of effective interaction parameters which reproduce these effective scattering lengths of lambda proton. And notice here that the spin singlet scattering length is changed according to the cases, whereas the spin triplet scattering length is fixed in all the cases. Then the results in the bottom panel shows that in case 1 and 2, one proton emission can happen from the 1 minus and 2 minus states both. But the resonance width really depends on the effective interaction strength. On the other side, in the case 3, I confirm that the one proton emission from the 1 minus ground state is forbidden. Namely, one proton emission cannot happen because in that case, simply the lambda proton interaction is strong enough to bind one proton. And in the case 1 and 2, the one proton width is predicted as, roughly speaking, 0.01 to 0.1 MeV. And this corresponds to the 10 to the minus 21 and to 10 to the minus 20 seconds. And let's compare this time scale with the lifetime of lambda particle inside the nuclei, and that is 10 to minus 10 seconds. Namely, comparing the one proton emission and the self-decay of lambda particle, one proton emission happens much faster than the self-decay of lambda particle. And for these 1 minus and 2 minus states, the result can or cannot be sensitive to the spin singlet lambda proton interaction.
So let me summarize my presentation today. So as my conclusions, first, one proton emission width of lithium lambda 6 is predicted as these numbers for an empirical lambda proton scattering length. However, this result is really sensitive to their hypernuclear nucleon attraction strength. And conclusion second, for 1 minus state, if the spin singlet hypernuclear interaction is enough strong, 1p emission can be forbidden. For 2 minus state on the other side, it is not sensitive to that interaction. Anyway, one proton emission can help the investigation of hypernuclear interaction. And for future works, actually there are many things to do. First, I want to try more realistic hypernuclear interaction, as well as not only for lambda hyperon, but also for the other hyperons. In many hypernuclear systems, including beyond the three-body model, remain an effect of the three-body force, tensor force, spin-dependent charge symmetry breaking, blah blah blah, are also waiting for their forthcoming studies. Thank you very much for your attention.